PCG Patiala. I am here to present a lecture on trees that is part of data structure. So first we will define what is a tree. Tree is a finite set of one or more nodes such that there is a specially designated node called root called root. The remaining nodes are the partitioned into n greater than 0 disjoint sets T1, T2 up to Tn, where each of these sets is a tree. We call T1, T2 up to Tn subtrees of that root. First we will study an example of tree. We will study the British Constitution, where crown is the root of the tree, and the branches of the crown are Church of England, Cabinet, House of Commons, House of Lords and Supreme Court. Now again there are sub parts of these branches, like we will discuss Cabinet. In Cabinet there are other subtree, that is ministers, and ministers is again divided into two parts, that is country council and metropolitan police. And again country council is divided into two parts, that is rural district councils and country work councils. So this is the tree. As we know, in general, what is a tree? Every tree has a root and it branches. So in data structure we study trees. That tree is also similar to the common tree. There is one more example in form of computer terms, or we say operating system, that is Unix Windows file structure. Like in Unix, there first is root directory, that is user root in courses. It is the file structure of Windows or Unix. It represents how files and directories are stored on the disk. In every operating system there is a tree structure, like first is root directory and there are sub directories in that directory, and in every directory there can be directories and files. Like blue rectangles are shown as files and black rectangles are shown as directories of the structure. There is a user root courses is a root directory, and then there are two subdirectories of this directory, that is CS016 and second is CS252. And for CS016 there are three subparts. Out of these three subparts, one is the file, that is grades, and two are the directories like homeworks and programs. And again homework is further divided. Homework is a directory, and this directory contains files, that is homework 1, homework 2 and homework 3. And then again program is a directory, and the directory program contains three files, PR1, PR2 and PR3, that is program 1, program 2 and program 3. And in second branch of the root directory, that is CS252, contains two subparts, that is one project, second is grades. Projects is a directory and grades is a file. And projects is again divided into two directories, that is papers and demonstrations. Papers directory paper have two files and demos has one file. Papers like buy low and sell high, and demos have one single file, that is market. So what is this? This is a tree structure of a operating system. You can say Unix and Windows both follows these data structures. Now we will discuss a few common things about the tree. Levels, like levels and depth. In the given tree there are 13 nodes. Node is a single value, or you can say a single point. We can count in this given tree nodes A, B, C, D, E, F, G, H, I, J, K, L and M. These are the nodes of this tree. There A is the root of this tree. Now we will discuss in coming slides degree of node, leaf node, non-terminal, parent, children's, what are the siblings, what is the degree of tree, ascendance, level of the node and the height of a tree. The degree of node is the number of subtrees in the node. The degree of a tree of a node is the number of subtrees of the node. Like in previous example, in this given tree is if we take node A, then its degree is 3 because it has B, C and D subtrees. Now the node with degree 0 is a leaf or terminal node. The node with a degree 0 is a leaf or terminal node, and it means the node having no child is a leaf node. A node that has subtree is the parent of the root of the subtree. Would we say any tree or subtree, the root node is known as parent of that tree. It may be a main tree or it may be a subtree. The root of these subtrees are the children of the node. Children of the same parent are siblings. Like in this example, for B, C, D are siblings because all these three nodes are children of the node A, and E and F are also siblings because these are also children of B. Now H, I, J are also siblings because these three nodes are children of D. And ascendants of a node are all the nodes along the path from the root to the node. Now we will discuss tree properties. As we know, what is a tree? Tree is a collection of nodes. These nodes are arranged in a tree manner, having a root and again child nodes and subtrees. Now we will examine these properties on behalf of this example. Taking example this tree, number of nodes in this tree, we have 8 nodes: A, B, C, D, E, F, G, H, I. So these next is the height of tree. Height of tree is the total number of levels in the tree. Like in this, first level contains node A, second level contains node B and C, third level contains node D, E and F, fourth level contain the node G, and the last level, that is fifth level, contain the node H and I. So in this tree we have height 5, and as we know what is root, in this tree A is known as root of this node, root node of this tree. Now leaves are those nodes having no subpart, or we can say no children. In this example, D, H, I, F and C are leaves. So we have 5 leaves. Number of levels in this tree, as we have already counted, is 5. Now what are the siblings? Siblings of E are D and F, because all these 3 nodes D, E, F are on the same level. So these are the siblings. D and F are siblings of E. Right subtree of the root node. As we know, A is the root node, and right subtree of this root node is C. Now we will discuss the representation of trees, how trees are represented in memory. Trees can be represented as a sequential list, or it may be represented as linked list. Like the root comes first, followed by the list of subtrees. In the previous example, as A was the root and B was the left subtree, and then again E, D and F. In this manner, in every subtree we will take root as first and followed by list of subtrees. Now we will discuss what is a node of a tree. Node is a single unit. Every node of a tree contains object and children. Object is useful information. It may be represented as a node of linked list. In this, every node contain object. Object is the value which is being we can say data, and first is and all other parts are the links to the children of that node, or we can say points to the subtrees of that node. Now this is left child right siblings. It represents a tree with having A is a root and has no right child, and it has single subtree, that is B. Again further, B has 2 subtrees, E and C has again G and D are as subtrees. This is known as left child right siblings. Now we will study what is binary tree. Binary tree is a finite set of nodes. that is either empty or consists of a root and two disjoint binary trees called the left subtree and the right subtree. In binary tree we will have either an empty or consists of root and two disjoint binary trees called the left subtree and right subtree. Any tree can be transformed into binary tree by left child right siblings representation. The left subtree and the right subtree are distinguished. Now we will I will tell you maximum number of nodes in BT. The maximum number of nodes on level I of a binary tree is 2 raised to power I minus 1, that is where I is greater than or equal to 1. The maximum number of nodes in binary tree of depth k is 2 raised to power k minus 1, where k is greater than or equal to 1. Now this is the samples of tree. First is skewed binary tree and second is complete binary tree. In complete binary tree we have A as root and two subtrees B and C. Again B and C are subtrees, and where B is root it has two subtrees D and E. Again C has two subtrees F and G, and in as we have D as part of B and D has two G and H and I as subtree. So as we can see that every node either is empty or have two nodes, two subtrees. This is the representation of a tree. First is a sequential representation of skewed binary tree and second is the complete binary tree. Like A is represented at first location, B at second. As A has no right subtree, so third part is empty, third position is empty. Again fourth represents C, fifth and sixth are empty because of it doesn't B doesn't have any subchild and C doesn't have any subchild. Again D comes on point 8th and E comes at last at 16. So the disadvantage of this skewed binary tree representation is it's waste the space, memory space is wasted a lot in this, and insertion and deletions are also tough to perform in this representation. And second one is the complete binary tree. Here all the nodes are placed in a sequenced manner and no memory wastage is there. So this is the linked representation of a tree. In linked representation, every node has three parts. One represents the data, one represents the pointer to left child, second and third represents to pointer to right child. So as we will, if we will implement it in C, it will be constructed using a structure. We will construct a node having three data members. First is data, type of integer, and second and third data members are of pointer type. They will point to left child and right child. Those are left child and right child may be leaf nodes, it may be a subtree. This is the structure of a node. First part points to left pointer, second then data, then value and right pointer. It may be enumeration on a structure, it may be a structure node. Now we will discuss full binary tree versus complete binary tree. A full binary tree of depth k is a binary tree of depth k having 2 raised to power k minus 1 nodes where k is greater than equal to 0. A binary tree with n nodes and depth k is complete if its nodes correspond to the nodes numbered from 1 to n in the full binary tree of depth k. As we can see in the diagram, a complete binary tree and second is the full binary tree of depth 4. Both of the trees have depth is 4, number of levels are same, but in full binary tree at each level every subtree go up to last level. Now we will discuss what is binary tree traversals. Let L, V and R stands for L stands for moving left, V stands for visiting the node, and R stands for moving right. There are 6 possible combinations of traversal. LVR, that is moving left, then visit the node and then moving right. LRV means moving left, then moving right and then visit the node. Next is VLR. We visit the node, then go to left child, then go to right child. Next is VRL, that is visit the node first, then go to right child, then go to left child. Next one is RVL, that means first visit the right node, go to right node, then visit the current node and then go to left. Last one is the RLV, that is go to right, then go to left and then again visit the node. Adopt conventions that we traverse left before right, only 3 traversal remains. That is LVR, LRV, VLR. First is LVR. LVR is go to left, then visit the route, then go to right. That is called in order. After that LRV, that is also known as post order. Go to left, then go to right and then go to route, visit the route. And the last one is VLR, that is visit first, then left, then right. That is called pre-order traversal. In order traversal, when we implement it in C or C++ or any other programming language, in order traversal, we place the operator in center and operands are on the right and left side of the operator. And in pre-order traversal, operator comes first, after that operands come. This is an example of in order and pre-order traversal. Like in first tree, first is the is not a complete binary tree, second is a complete binary tree. As we will if we will in second tree, if we will traverse it as a pre-order, then BEF is a subtree. If we will traverse this tree as an in pre-order, first we will take B. B is what is the first we will take root of the tree, then we will take left, then right. So it will become BEF. And in second, if we have C as a subtree and we are going to traverse as pre-order C subtree, then first we will take C, then we will take G. And in the last one, that is D having root subtree, first will come D, that is root of the tree, then H, I, J. So the complete pre-order traversal sequence of this tree will become A, B, E, F, C, G, D, H, I and J. And in order traversal for this tree will become E, F, B, G, C, H, I, J, D, A. As in every tree in order traversal, root will become in center and right and left subtrees or leaf nodes will come. So this is the procedure for post order traversal. In post order traversal, the operator, or we can say root, will come after the operands. We will take the example of arithmetic expression using a binary tree. For example, in order traversal, this tree will be traversed as A divided by B. It is an in order traversal, so A and B are two operands and division is the operator. So A and B will A will become first, division in center, and B at the right side. Then there is an multiplication with C, and the result of these will be multiplied by D, and all the results of the from root, left subtree to right subtree, will be there will be addition. It is also called infixed notation for arithmetic expressions. And for pre-order traversal of this tree, there will come addition, multiplication, then division, and after that all the operands will come like A, B, C, D and E. And we will, if we will study postfix expressions, then plus, addition, then multiply E, then multiply D, division, and then C, A and B. Now we will study what is Euler tour of traversal. It is the generic traversal of a binary tree. The pre-order, in-order and post-order traversal are special cases of the Euler tour traversal. What is Euler tour? It is the walk around the tree and visit each node 3 times, on the left, from below, on the right. So what it is the journal traversing of all the nodes, all the leaf nodes one time, and all the root node, if it is a subtree or it is a main root, they will be traversed as 3 times in a single traverse. Now we will discuss what is a binary search tree. A binary search tree is a binary tree with the following properties. So this is an extension to binary tree. All items in the left subtree are less than the root. So we can say it is a sorted tree or it is a sorted data structure, because all there is a condition that all the nodes of left subtree will be less than the root, and all items in the right subtree are greater or equal to the root. Each subtree is itself a binary search tree. So again, if we will study any subtree of the binary search tree, then that tree will also be a binary search tree. So basic property of a binary search tree: the left subtree contain key values less than the root, as we have discussed. The right subtree contain key values greater than or equal to the root. These are the examples of binary search tree. As in first tree we have the root node 20, and in right subtree we have values 25 and 22. All these values are greater 25 is greater than 20, but the subtree right subtree is not a binary search tree, because its subtree have a right child that is having value 22, that is less than 25. So it is not a binary search tree. Second example is the tree having root 30 and left subtree have value 5 and right subtree have value 40. So this is a complete binary search tree. And the last is having root 60. Its root is 60. It's but all the values in the right subtree are not are greater than 60. So it is also complete binary search tree. So in figure we show that what are the criteria for this binary search tree. If we have the value k for root, then all the values on the left subtree will have less than k, and all the items on the right subtree will have value greater than k. Again, examples of binary search tree, like A is a empty tree having not empty, having only root node. Then B is the tree having root node 17 and 2 subtrees having value 6 and 19. And C is a tree having node 17, root node 17, and on left 6 and 3 are the values. D is a tree having root node 17, and right subtree has 19 value, and left subtree have 6 as root node, and it is again subtree that having value 3 as left node and 14 as right node. So A and B complete and balanced binary trees. D is nearly complete and balanced binary tree. Then C and E are neither complete nor balanced tree, because this does not fulfill the criteria or conditions of a binary search tree. All these given A, B, C, D trees are the invalid binary search tree, because these trees does not fulfill the criteria of binary search tree. It should be an sorted tree. All the values at the right side should be greater than root, and all the values at left side should be less than the root. Now, what are the operations of BST, that is binary search tree? We discuss 4 basic BST operations. First is traversal, second is searches, third one is insertion, and fourth is deletion. 3 types of traversals of a binary search tree is possible. First is pre-order traversal, second is in-order traversal, and third is post-order traversal. In pre-order traversal, first we will visit left subtree, then right subtree, and then we will in pre-order first we will visit root, then left subtree, then right subtree. And the second traversal is in-order traversal, most commonly used traversal for any expression and any data structure. First we will traverse left subtree in order notation, and then we will traverse root node, and after that we will traverse right subtree. So what is this? Visit left, then root, then right. And in post order traversal, first we will visit the left subtree, then right subtree, and then root. So what it comes then in pre-order, we will again discuss what is pre-order. In pre-order, left, then root, then right, and in end order, left, root, then right, and in post order, left, right, then root. So what is the result? In pre-order, root comes first, in order root comes in center, and in post order root comes after all this left and right subtrees. Again an example of binary search tree. As we have a tree having 7 nodes. Out of these 7 nodes, one is the root node, that is having value 23, and right subtree having root 44, and left subtree root having value 18. In first subtree having root value 18 have again 2 nodes, left is 12 and right is 20. So it fulfills the criteria of binary search tree. Every right node has value less than root, and every left subtree or subnodes have value less than root. Now we will take the example of pre-order traversal of a binary search tree. First, if we will traverse this tree in pre-order traversal, it will become 23. First the root node becomes. Then we will traverse the left subtree, so it will become 18. Then its left node is 12. Then its right node is 20. So the first part of the tree is traversed as 23, 18, 12, and 20. And after that we will traverse the right subtree, that is having root 44. So what we will take first is 44 as root of the subtree, then we will take 35 because it is the left subtree, and then we will take 52 because it is the right subtree. So the overall pre-order traversal will become 23, 18, 12, 20, then go to left, that is right, that is 44, 35, and then 52. Now we will study post order traversal for the same tree. So first it is an we will take in post order traversal, root comes at the end. So we will first we will take